Here we have a problem of moving a force on a rigid body. So we can see we have our rectangular plate here, and we have a force that has 15 kilonewton and it's acting on this corner down here. And we are asked to find the resultant force and the moment if we want to move everything from A over up to B, not over but up. B would be up here. All right, now how do we do that? And we're supposed to give the resultant force as a Cartesian vector. Okay, let's get started. All right, so we can say A. We know that our FR, right, is the sum of all forces. Now the only force that's acting here is F, so FR is going to be equal to F, which means we have to write F as a Cartesian vector. So we know that is just the unit vector of F times the magnitude. And the unit vector of F is given through us by this angle here. Now we have to be a little careful. Usually we do cosine in X and sine in Y, but now the angle is up here, not down there. All right, so we have to do it the other way around. So the X component will be going in this direction, so that would be sine. So we would get sine of 62 degrees times I plus cosine 62 degrees times J, and all that times 15 Newton. And if we put that in the calculator, then we get 13.244 I plus 7.042 J Newton. Now let's make sure we get the signs right. Yeah, that's good. You see, right, we have our X and Y coordinate system here, so it's positive X, positive Y. So that is good. So that will be our resultant force. Basically just the force itself. And now we have to find the moment, right? So we have to have the moment of all the forces that are acting on our plate with regards to B, because that's where we want to move it. The only force that we have is F, and we've already taken F and split it into components, right? We can say this is Fx and Fy. Right, so we can see that Fy is not going to have a moment arm because the line of action goes straight through B. And we can see that for Fx, it will be just this distance here, right? So that would be 200 millimeters is 0.2 meters. Now how does it turn? It turns this way, right? If I hold my B here, right, I have my force turning in around this direction. So that would be counterclockwise, so positive. So our MCB is then just our Fx, which is 13.244, or if you want to be exact, we can say that be 15 kilonewton times sine 62 degrees. That way we don't do too many rounding errors. And then we said our moment arm would be this distance here, right? Because my line of action is like this. So it'd be 0.2 meters. And if I plug that in, then I get 2.6488 Newton meters. Oops, that's a meter. Which means it is turning counterclockwise. Counterclockwise. All right, that was part A. Now for part B, we're supposed to do the same thing, but now instead of moving it to B, we're moving it to C right over there. Well, it doesn't change what our sum of forces is, so we can say FR same as before, is 13.244 I plus 7.042 J Newton. Right, that's the same. But now, of course, our moment is probably going to be different. MCC. So let's see. In this case, both our x and our y components are going to have a moment arm, right? If this is my line of action here of fx, then I know has a distance of 0.2. So we can say this is equal to fx times 0.2 meters. Now let's see, how does it turn? Fx will be turning this way, so that would be positive. So clockwise is positive. And then Fy, moment arm would go all the way over there, so it'll be Fy times 0.5. Y times 0.5 meters. Weird looking M. And let's say it is turning counterclockwise as well, so also positive. Let's put a plus here. So that means we get, we can write 15 kilonewtons times sine 62 degrees times 0.2 meters, right? That'd be my Fx is sine 62 as 15 kilonewtons times, not kilonewtons, just regular newtons. Let's not get too fancy here. So 15 Newton. So 15 Newton times sine 62, right? That's my Fx. And then Fy was cosine 62 degrees, and now the distance was 0.5 meters. And that gives me a value of 6.1699 Newton meters. And because it's positive, it is turning counterclockwise. Counterclockwise. And with that, we have calculated what it would look like if we move this force that's acting at A either to B or to C.